Hello, I'm Tien. I'm a PhD student at CVIU Lab, University of Arkansas. This is my presentation about the paper entitled BIMA, Bijective Maximum Likelihood Learning Approach to Hallucination Prediction and Mitigation in Large Vision Language Models. Initially, large vision language models, LVLMs, have emerged at an accelerated pace in various domains, demonstrating remarkable success in numerous practical applications. These highly capable models excel in facilitating interactive conversations with users, providing them with the convenience and versatility to manage a wide range of daily tasks. However, their reliability and trustworthiness are critical, yet they are plagued by the notorious technical challenge of hallucination. Next, let's talk more specifically about hallucination in LVLMs. Hallucination happens when the machine's response is semantically coherent, but part of it or the entire is misaligned or inconsistent with the provided context. The context can be the given text prompt or the visual content. This issue results in a lot of severe consequences, such as spurious decision-making or the dissemination of misleading information. Therefore, it is imperative to come up with solutions to mitigate the issue of hallucinations in LVLMs. To this end, we propose an approach to mitigating hallucinations in LVLMs named BIMA, with the idea of mapping each response to its corresponding degree of hallucinations. Our motivation stems from the intuition that the closer the responses from the machine and human are, the less hallucinations will occur. In other words, whenever the responses are favored by users, hallucination will be less likely to happen. Therefore, we propose to model this situation by a distribution of desirable responses and to learn a bijective mapping between this distribution and the machine's responses. The ultimate goal is to bridge the gap between the machine's responses and the desired ones. To summarize what we've been talking so far, we propose to use Bijective Maximum Likelihood Learning, or BIMA for short, to resolve the problem of hallucinations in LVLMs. Specifically, we use the theory of normalizing flow to model the reference distribution, which is defined as the distribution of non-hallucinated responses. To visually illustrate the reference distribution, let's take a look in the following diagram. As can be drawn from our design, incorporating this reference distribution helps the model learn its response's degree of hallucination more effectively. Move to the main method of BIMA. This is the overall framework of our proposed approach. Particularly, the baseline LVLM has two main components, which are the visual encoder, will be frozen during training, and the large language model that will be fine-tuned. In the decoding phase of BIMA, the response will be mapped referred to as reference distribution via calculating the bijective loss. At the end of this process, the output will become not only coherent, but also more aligned with the textual and visual contexts. Next, we will discuss about fine-tuning BIMA. The learning objective for our approach is expressed as follows. The parameterized model by theta is optimized by the autoregressive loss, which can be seen in prevailing LVLM's framework, and the proposed bijective loss. The data used for training procedures is from the supervised fine-tuning dataset, which is publicly available. Particularly, the data is provided by LVLM 1.5 to create a one-hot vector dataset for the bijective mapping model, as well as to fine-tune the model in the pipeline of visual instruction tuning. We also adopt LVLM 1.5 model as the baseline for our experiments. To conduct experiments in our paper, we use the following benchmark datasets. First, we use POPE benchmark, which is the visual question answering benchmark that is frequently used in investigating hallucinations in LVLMs. POPE benchmark uses questions designed as yes-no questions. It also has three different settings based on the addition of negative samples, which are random, popular, and adversarial. Next, we use CHAIR benchmark. The questions are more about visual captioning, and the benchmark consists of two evaluation levels, which are sentence level and image level. The pertinent metrics are used, CHAIRS and CHAIRI, with the following definition. Here we show the quantitative results evaluated on the CHAIR benchmark dataset. Compared with prior work, our proposed BIMA reduces the CHAIRS and CHAIRI metrics to 34.4% and 9.6%, which is 7.6% and 2.6% improvements respectively. This showcases the effectiveness of BIMA on reducing hallucinations and captioning benchmark. And here is the quantitative results while evaluating BIMA on POPE benchmark in comparison with prior work. Our proposed BIMA can surpass prior work in adversarial setting while maintaining competitive performance on random and popular splits. Let's now look at the qualitative results of our proposed BIMA juxtaposed with the baseline law of our model. As depicted in the figures, BIMA produces more meaningful responses with fine-grained details and less hallucinated objects. This concludes the good performance of our proposed BIMA in mitigating hallucinations in LVLMs. That is the end of my presentation. Thank you for your attention.